I am H.S. Mayuranga. I am a PhD candidate at Department of Civil Engineering, University of Peradeniya. My research topic is shear and degradation behavior of rail ballast with different interfaces. Let's get a background idea about this study. As you all know, railway transportation is one of the major transportation modes in many countries. When we consider railway track systems, ballasted track is the traditional and widely used railway track system in many countries, including Sri Lanka. So in this figure, you can see a conventional ballasted track in Sri Lanka. When we consider a cross-section of this particular track, at the top, rail and sleepers are there. Under that, the ballast layer is there. Under the ballast layer, sub-ballast or concrete bridge deck is there, depending on the track location. Ballast layer is considered as the main load-bearing structure in a ballasted track, and that provides structural support against high dynamic stresses, facilitates for better drainage, provides lateral resistance, as well as minimizes the growth of vegetation. Due to the presence of high speed and heavy trains on existing ballasted rail tracks, the inclusion of undersleeper pads to improve the track performance is an established practice in many countries. These undersleeper pads are known as energy absorbing shock mats, and they are attached to the bottom of the concrete sleeper as shown in this figure. In this figure, you can see the attachment of undersleeper pad to the concrete sleeper using epoxy glue. When we look at the cross-section of a ballasted track, the sleeper ballast interface can be identified as shown here. It is required to maintain a proper contact between sleeper and ballast at sleeper ballast interface in order to effectively transfer the train load through the sleeper to the underlying layers. Depending on the type of sleeper used in a ballasted track, different sleeper ballast interfaces can be identified. Generally, three major types of interfaces can be observed. When timber sleepers are used, timber sleeper ballast interface is there. When concrete sleepers are adopted, concrete sleeper ballast interface can be identified. Also, when undersleeper pads are attached to the bottom of the sleeper, undersleeper pad ballast interface can be observed. Also, in the ballasted track, the shear strength capacity of ballast plays a major role in maintaining the lateral stability of the railway track. At the same time, different sleeper ballast interfaces significantly influence the overall shear behavior of the ballast layer. Not only that, ballast particle breakage is also significantly affected by the surface type of sleeper ballast interface. Therefore, it is important to investigate the shear strength parameters and the degradation behavior of railroad ballast with different sleeper ballast interfaces. Therefore, in this study, large-scale direct shear tests were conducted to understand the shear and degradation behavior of ballast at different interfaces such as ballast interface, timber sleeper ballast interface, concrete sleeper ballast interface, and undersleeper pad ballast interface. For that, the large-scale direct shear apparatus designed and built at the Geotechnical laboratory was used. Here you can see a drawing of the large-scale direct shear apparatus, and this figure shows a photograph of the apparatus. This particular apparatus can accommodate a cylindrical ballast sample of 400 mm diameter and 300 mm height. The bottom half of the cylinder can move laterally under a predefined normal load by using the hydraulic jack attached to the system. All the displacements are measured by using the displacement transducers. Also, the load is measured using the load cell attached to the system. With that, I am going to explain the test arrangement used in this study. Four different test conditions were considered, and each test specimen was tested under 30, 60, and 90 kilopascal normal loads. In the first test setup, the cylindrical specimen was completely filled by ballast to represent the shear behavior at ballast interface. In the second test setup, the bottom half of the cylinder was replaced by a timber sleeper material to represent the shear behavior at ballast timber sleeper interface. Similarly, in the third test setup, the bottom half of the cylinder was replaced by a concrete sleeper material to represent the shear behavior at ballast concrete sleeper interface. Finally, the undersleeper pad was attached to the concrete sleeper and placed at the bottom half of the cylinder to represent the shear behavior at undersleeper pad ballast interface. When we consider test materials, in this study, fresh ballast, timber sleeper, concrete sleeper, and undersleeper pad materials were used. Fresh ballast material was collected from Gambola Railway Storage Yard of Department of Railways, Sri Lanka. Ballast material was washed and air dried in order to remove the dust and fine particles attached to the ballast aggregates. The ballast samples were prepared confirming the particle size distribution following the Indian standard gradation, which is currently adopted for Sri Lankan railway tracks. Here you can see the test ballast gradation and upper and lower limits of Indian standard gradation of ballast. Also, this figure shows the graded ballast samples considering 4 different particle sizes. Here you can see the timber sleeper and under sleeper pad attached to the concrete sleeper. With that, I am moving to the results of this study. Here you can see the variation of shear stress with shear strain of different interfaces for 30, 60 and 90 kilopascal normal loads. As expected, for all three normal loads, the ballast interface exhibits the highest shear strength compared to other interfaces. This could be a result of high interlocking nature of newly placed angular ballast particles. When we consider the shear behavior of different sleeper ballast interfaces, ballast concrete sleeper interface provides the highest shear strength, while ballast timber sleeper interface exhibits the lowest shear strength. The reason for this result could be the variation in surface roughness of different interfaces. Here you can see the variation of normal strain with shear strain of different interfaces for 30, 60 and 90 kilopascal normal loads. Based on the results, it can be observed the dilation behavior of test samples. The maximum dilation can be observed for ballast interface. Also, the dilation behavior has been decreased with the increase in the normal load. However, ballast timber interface does not exhibit dilation behavior. The reason could be the less surface roughness of the timber surface, and that influences the ballast particles to slide on the timber surface instead of rolling. Here, this figure shows the Coulomb failure envelopes developed based on the results of shear behavior for each interface. Based on that, the friction angle values were calculated for each interface. Here you can see the variation of friction angle for each interface. The highest friction angle value can be observed for the ballast interface, and the lowest value can be observed for the ballast timber interface. Also, ballast concrete interface has a higher friction angle value compared to ballast under sleeper pad interface. Also, here you can see the reduction percentages of friction angle for each sleeper ballast interface with respect to ballast interface. At the end of each test, ballast samples were sieved and obtained the particle size distribution in order to evaluate the ballast particle breakage. Then the ballast breakage was calculated for each case based on the ballast breakage index proposed by Navaratnarajah and others in 2005, as shown in this figure. According to that, the ballast sample exhibits the highest particle breakage, and ballast under sleeper pad sample shows the lowest particle breakage. Also, the particle breakage increases when the applied normal load increases. Here you can see the reduction in ballast breakage index of sleeper ballast samples with respect to the ballast sample. About 80% reduction of ballast breakage can be observed for ballast under sleeper pad sample. However, only about 25% reduction can be observed for ballast concrete sample. At the same time, ballast timber sample exhibits a higher reduction compared to ballast concrete sample. Therefore, it is clear that the application of under sleeper pad in ballasted tracks significantly reduces the ballast degradation. With that, I am moving to the conclusion of this study. A large-scale direct shear tests were conducted to evaluate the shear and degradation behavior of ballast with different interfaces. Ballast and ballast timber interfaces exhibited the highest and lowest shear strength values respectively. The shear resistance of the ballast under sleeper pad interface was less than the ballast concrete interface. The highest ballast breakage was observed in ballast interface, followed by ballast concrete, ballast timber, and ballast under sleeper pad interfaces. Therefore, the use of under sleeper pad attached to the concrete sleeper will provide better performance of the railway track. With that, I would like to acknowledge the support provided by Accelerating Higher Education Expansion and Development Operation funded by the World Bank and the University of Peradeniya Research Grant. Also, the support provided by the District Engineer of Nanoy Railway Office and the staff of Navaratnarajah Railway Unit of Department of Railways, Sri Lanka are highly appreciated. These are the references I cited throughout the presentation. And with that, I conclude my presentation. Thank you very much.